There we go. All right, hello. So thanks for the introduction. As Travis mentioned, I'm going to be talking about token-based architecture. It's kind of a buzzword that I put together to describe what I'm talking about, but really this talk is sort of a deep dive on how the little detail of token design can actually play a big role in how you're able to implement a more complex architecture like Johannes was showing towards the end of his presentation. So, hello, my name is Kevin Nelson. This is my Twitter handle and my email address and how I look on most of the internet. Looks like some pixels may have gotten caught in the tube there, but that's what you'll see when you look at it. I'm currently an independent contractor working in developing API things for a couple of clients. My history is from a music streaming service in San Francisco called Rdio. And I was working on their API for a couple of years as a developer evangelist and implementing features. So this presentation is really about sort of some of the things that I've learned in the course of building out API services and API platforms. So let's get started. What is a token? How many of you have built systems that require tokens to use? Good chunk of the audience. All right. And of you, how many just generated a random string and threw that string in the database? Only a small percentage, really. Wow. That's impressive. Maybe we can have some interesting conversations about that later. So before I dive too deep, I'm going to talk a little bit about my personal API philosophy. And this jives a little bit with some of the stuff that's previously been said and actually contradicts it a little bit too. And my advice, in addition to hiding complexity and abstracting things away, I actually want to say don't overthink it. Your API is actually not that complicated of a concept, and there's really only, in my opinion, two pillars of what an API is. So if you're building an API, you need to do these two things. You need to first manage access control, and second, provide data stability. So the goal in designing your API is to design your access control in a way that encourages data stability. So what do I mean by access control and data stability? Access control is user identity, which means you have some kind of system to authenticate your user or your apps. And it's some kind of permissions model that says, hey, this user has access to modify or read this. So if you think about Facebook, this is, I have an email address and a user account on Facebook that I use to authenticate. And then when I try to look at someone's photos that I'm not friends with that are private, I don't have permission to do that. Or if I post a photo, I'm allowed to do that to my own account, or whether or not I'm allowed to post a photo to someone's page or something. So that's the first part. And data stability is this general bucket that I include a lot of things like accurate documentation, consistent response format or API versioning. And I also put into data stability service uptime and availability. So I think the eventual consistency point from earlier is an interesting note, but I think that consistency and responsiveness are actually part of the same thing. So if your service goes down, your data is no longer consistent and you've got an error, and hopefully it matches something in your documentation that describes what you do when your system goes down. There are plenty of resources about how to document your API and how to try to provide consistent response formats. So I'm actually not going to be talking about those. I'm going to be talking about user identity permission and how that encourages your service uptime, your scalability, and your availability. So let's look at some common archetypal API architectures. These are three sort of common models that I've seen in the world of APIs. You have the happy accident. the front desk, and then lastly, Metropolis. So the happy accident is if you have a website, you have an API. Congratulations, you can all go home now. This is I curled your HTML address and scraped your HTML to get the data I needed. And this is actually not the worst thing in the world, except for the data stability part, because if this is on your web page and you decide to have a web redesign and your markup changes, then all of your CSS selectors change and you've broken the app. This is also a bit of a problem if the data is behind some kind of authentication. So this is kind of what the happy accident architecture looks like, where your API requests and web requests are actually one and the same. It's just how they're being used. On the web requests from a browser, there's a person behind there looking at the web page. The API requests is a program grabbing all of the markup from your site, parsing it, and getting the data out that you need. So I've actually done this before. While I was at Rdio, I built a scraper for the Billboard music charts. How many of you are familiar with Billboard magazine? Everyone here, yeah? So they have a website which publishes their charts and has Rdio IDs to play them from their site, but they don't actually have an API. So I built a little scraper that looks kind of like this, where you have to do a good bit of XML, you have to do a good bit of CSS parsing, and ultimately I was able to build a wrapper, build a library that parsed their site and build an API on top of that that had one or two Python methods that would list the types of charts they had and let you grab the Rdio IDs from the chart and create a playlist out of it. So I was able to take a published, documented, and supported API and mash it up with a unpublished, undocumented, unsupported website, because HTML, as for all of you who were in Irakli's talk earlier, you already have an API on your website. So, as I mentioned a little bit, the unhappy accident is website updates that you're not in control of can break your implementations. And if any of this data that you're scraping is behind some kind of authentication, for example, if you wanted to scrape your banking data for your own personal reasons and build something like a mint.com for yourself, then you have to deal with usernames and passwords and all sorts of encryption, and it's a major headache, and that was the problem that OAuth was originally designed to solve in the first place. So that's the happy accident. The front desk is sort of, I think of this as like visiting a hotel. So how many of y'all are from out of town visiting Stockholm today? How many of you are staying in hotels? So you had to check in at your hotel, right? And you got a key card to your room. This is sort of what I consider like the API gateway model, where you have this gateway that brokers all of your API requests. It resolves your authentication. You can buy these from many companies who I won't name, but some of them are sponsoring the event. But gateway as a service exists as a provider, so you can maybe save money that way or save development time, and get to market sooner. And this looks a little bit differently. Like, you still have your web servers, you can build your single Rails app to iterate fast, or you can build your Django app or whatever your framework of choice is. You build up your web servers, you prototype fast, and then you stick an API gateway out on the side that proxies all of the requests to your API server. There's also one of the things I saw interesting that I will call out by name because it's open source is this service called tyke.io that's an API gateway built on Go that looks very interesting. But it does app authentication, user authentication, rate limiting, and analytics. So that's basically what you need to do as an API provider. You want to provide all of your callers, all of your customers with sort of what their usage looks like, what methods they're calling. You want to look at that internally to see how you're doing and how you're performing. So this has its ups and downs. It's easy to develop quickly. It's easy to iterate on because you're just building your web servers. It still has some overhead because now somewhere in your web servers you have to integrate with this gateway library. So it's not totally free, but it also has potentially rigid architectural constraints. So if you're using a service that behaves in a certain way, then you're always going to have those requests coming in from that service. It introduces a single point of failure for all of your API consumers. It's possible to parallelize, but at the same time, you run into scaling issues because how are you parallelizing your API gateway? You get into some potentially costly situations if you buy in early to get to market early and then wind up having to pay recurring service fees, depending on how long it takes you to either get off of that service provider, whereas if you just built it yourself, you would have paid more up front, it would have taken you longer to get there, and then it would have been built and you'd be paying smaller maintenance costs. So this way is the common way that I've seen a lot of times, and it sort of grows into something that if you did actually build this API gateway yourself, you might say, well, okay, I want to split up my web servers now and have a more service-oriented architecture. I want to bring out search from here. I want to build this new service that doesn't actually rely on anything else. It just needs user IDs. I'm gonna build, basically think of Facebook messages. Like how much of Facebook messages does the messages service need to know about your actual Facebook account? It needs to know your user ID and your name and who you're talking to. And that's it. So when you want to break this out, maybe you put routing in your API gateway, which was something that your web services used to do. You can imagine how this might be built in a couple of different ways at a couple of different layers. You get to a point where you've got a routing desk, your user box does all of your user profile and authentication, you have a message server, you have a search server. Your specific applications obviously will have different needs based on what service you provide through your API. And finally, we have the METROPOLIS, which is the actual service-oriented architecture. And this is the thing that token design really plays a key role in, because if I go back a couple of slides, when you do this part, you have your app authentication. Most people, when they design tokens for access tokens or API keys or session cookies, they generate a string, they put the string in a data store somewhere, and they associate the string as a key with the value of a payload. So if you recall, sorry, I'm getting a little bit ahead of myself, so I'll get back to that in just a second, but the idea behind the METROPOLIS is that if each service knows how to handle API gateways, and can handle their own authentication, then your API requests can just hit these services directly. You can use them internally, you can use them externally, and then your individual service, each service has a front desk. So this is an archetypal pattern. The front desk is a recurring theme, right? You still have your authentication, you still have your authorization, you have your endpoint-specific logic. So how can we design tokens to turn the first two into a library that works fast and doesn't reintroduce the database as this single point of failure, where if you look at the timeline of your requests and what services they hit, you still get that bottleneck, whether it's the gateway or the database in your token validation. So with auth, we're looking at, can this user perform this action, and can this app perform this action on the user's behalf? So how do we abstract this? How do we build an API that handles this? Back to the definition of token, it's a thing that serves as a visible or tangible representation of a fact, quality, or feeling. So in our case, it's an opaque string container that represents some user that we have previously validated. So think of this as your driver's license. When someone checks your ID, yes, they look at your photograph to verify that you are you, but they also are verifying that the identification card came from a known and reputable source, that it's actually a government ID, or they recognize the university, et cetera. So how can we mirror that with tokens? If you checked into your hotel, for example, you have a key card. Imagine you had to go to the front desk every time you wanted to get into your room. Right? Like that's kind of the bottleneck that we're trying to avoid. So another way to do this is to generate as minimized of a payload as possible. So have a user ID, have some timestamps, have some identification there, and then serialize it, sign it, and encrypt it. So the HMAC and payload combination tends to be very common. If any of you are familiar with JSON Web Tokens, which I will refuse to pronounce because I think it's a horrible acronym and horrible pronunciation, but actually a really cool concept. The problem with JSON Web Tokens is that your payload data is in clear text. So if there's anything there that you wanted to transmit securely and someone were to intercept those packets, they would be able to look at that data, decode the base64, and see what data is sent. The HMAC signature prevents them from spoofing the token and changing the information because the signature will be invalid. But nothing actually envelopes that so that it's not visible to anyone who intercepts the traffic. So basically what you do is you build a library that has two methods. It has a generate token method that you provide a payload to, and it has a parse method that you give it an already generated token and it returns the payload for you. So this has the benefit of not having any database lookups, and you don't have to store your tokens. And even better if you're really, really performance hungry is that it's constant time because you're just running encryption algorithms. The one constraint is that you're sharing secret keys between each of those services. So you do need properly implemented crypto libraries, and you need a mechanism to share secret keys between your services. The other elephant in the room that many of you might be thinking about is revocation and logout. If you have not stored the token, how do you revoke its permission? And there are a couple of solutions to this that I'll talk about in just a second. Some of this relates to the payload value. So in my experience with one of my clients, we are doing the user ID that is sort of a UUID across all of the system. We're including the display name so that when the user is using a service or hitting HTML rendered by one of those node services, they're able to display their display name and avatar. And then we have some issued at and some expiry and a session ID. The session ID is not particularly relevant if you're doing API tokens, but if you're doing session tokens, that's one of the things that you can use to invalidate tokens that have been revoked or logged out. So we have a payload, we tokenize the payload, and the token looks something like this. The token is about 220 bytes, so it's not going to destroy your cookie space. The payload data is encrypted, and it's encrypted with two keys. So you need to basically lose both of those keys in order to have some kind of data leakage or spoofing. And because you've built a mechanism to share keys between servers, that means you also have a mechanism to rotate those keys as you go forward. So if you do an OAuth example, you can add scope to this, and then the new token is about 330 bytes. So let's talk about leaving Metropolis, logging out and revoking access. So first thing I want to point out about this is, when was the last time any of you logged out of a web page? Within the last 3 weeks, month? Like 3 people? What about the last 2 weeks? You guys log out a lot. Okay. How many of those were on personal computers rather than public computers? Really? Surprising. Okay. And how many of those things that you logged out of were not financial or extremely sensitive data services? Fewer. Okay, cool. So I haven't done thorough usability studies on this, and I would love to see or conduct this research, but my understanding based on the people that I've talked to is that logging out and revoking an API app's access are edge cases. They're not something that you do 90% of the time. And if you think about this, you're including an access token on every single API call. So if you have 100,000 API calls hitting your service in an hour, you're parsing that token 100,000 times an hour. You might have 100 users logging out or revoking the app in the same hour. So you've got this is based on my experiences. It's not a formal study, but it's more or less an edge case, and it's the sort of thing that is okay to make a little bit slower. So when you do deauthorize, you're going to hit this auth server, which is going to propagate a message to the rest of your services, and we did want to avoid storing this all in a single database bottleneck, but it's much easier and much faster to store the tokens that have been revoked than it is to store every single token. So instead of checking to see if the token is valid, you're checking to see if the payload has been deauthorized. And then what you do when you log out is you have each of these services in that library, store that either in memory or in a fast data store like Memcache or Redis, and you lower the token lifetime to be something like an hour or 2 hours. So depending on your needs, you can use this back channel to propagate token revocation and distribute secrets to your nodes. And you probably already have some kind of back channel communication like a message queue in your service anyways, which was something Johannes mentioned. So, in review, some general API philosophy about keeping things simple, some archetypal architectures, and how tokens can optimize those scaling experiences. And this is my last slide, but we're going to be doing that later. So instead, we'll say thank you.
Great.